Okay, so we have seen the greedy algorithm for job scheduling with deadlines, and we have established that in fact our solution is optimal. So now let's analyze its complexity and look at an optimization. So the first is to establish the complexity. So in our algorithm, the first thing we do is we sort by price. Right? We sort n jobs by price, and as we know, sorting can be done in time O n log n. So this is not the real bottleneck. The bottleneck is that we insert each job in the current solution. Right? So when we check feasibility, so we maintain J in sorted order of deadline. So at each point we look at the new job and we try to insert this job into the sorted list, and if we can meet the deadlines, then everything is fine and we proceed. So now what would be the worst case? The worst case is that each new job is feasible and has a smaller deadline. A smaller deadline than everything in J. So it has to go to the extreme. So we have to scan all of J from right to left in order to find the insertion point. Okay. So in the worst case, uh, checking feasibility of job I, okay, involves inserting in J of size I minus 1, and so this takes something like I minus 1 steps, because I have to step through I minus 1 positions before I find those insertion point. So overall, the sequence of inserts is now going to take me 1 plus 2 plus up to n minus 1. So the first step takes no insertions, the second step takes 1 insertion, and so on, and the nth step takes n minus 1 insertions. And this we have seen a long time ago is theta of n squared. Right? So we had sorting, which was O n log n, but now we have this insertion, which is theta of n squared. So therefore the final complexity, right, the final complexity is in fact theta of n squared. Right, so the bottleneck that we have is inserting each job in J, right? So we maintain J in sorted order and we have to insert each job in J. So, and the reason that this is really the reason that the bottleneck comes is because when we insert a job in J, all the existing jobs in J may have to shift by one. So the job starts off being scheduled at a given point, but as a later job comes, it might displace it to the right. And this is really what the effect of that insertion is. So wouldn't it be nice if we could schedule all jobs once and for all in an optimal slot, right? So we want a once and for all slot for each new job, right? So we have that we want to add job I with deadline di. Okay. Now suppose we can find the rightmost free slot before di. Okay. So let us call this slot, say, alpha I. Right. So alpha I is the rightmost free slot which is before the deadline. And so now what we would like to do is we would like to schedule I at slot alpha I. So by slot alpha I, we mean the time slot alpha I minus 1 to alpha I. Remember, each job takes one time slot. So this time slot is where we're going to put it. Now this is the rightmost slot which is free to the left of the deadline. And so we cannot possibly move this right. Okay. So we never disturb I after this. So we'll just leave it here. Right? So when it comes in, it gets scheduled as late as possible given the current constraints. And after this, we cannot modify this constraint because we know that no job is ever going to leave our system, right? It's a our greedy algorithm is monotonic. Once you put a job in, it stays, and we're going to keep it at the position where it came, and that position was the rightmost position it could have come in, so it's never going to move to the right. So just to remember, slot I denotes the time from I minus 1 to I, right? So this is what we mean by slot I, the time from I minus 1 to I. So now let Ni be the first free slot to the left of I, right? So this is the latest time slot that I can put without crossing I. So in general, of course, Ni is going to be less than or equal to I. If I itself is free, then Ni is I, but it could be something strictly smaller. Okay? So now we observe that suppose I is less than j and Ni is equal to Nj. That means that I have a situation where I have, say, position I and I have position j, right? And for both of them, the first free slot to the left is the same. Then for every intermediate slot also, this must be the first free slot, right? So none of them can find any slot which is further to right. So everything from I to j has the same left endpoint in terms of the first free slot to the left. So I will say that I and j are in the same set if Ni is equal to Nj, and this implies that I plus 1, I plus 2 up to j minus 1 and then j is one set, right? So if I and j belong to the same set and I is less than j, then everything in between must also belong to the same set. Now given a set k in general, it may not, initially a set may look like an interval, but we will, of course, sets are disjoint because two different sets cannot share an I. If two disjoint sets share an I, then both of them have the same Ni, so it's the same set. So given a set k in general, okay, I will say that f of k is the value Ni. That is the smallest, rather the largest interval free to the left of all of k. Right? So f of k is just that value which captures the largest time point which is free for everything in k. So now what I do is the following. Initially, notice that no job needs to be scheduled beyond the largest deadline. So I will assume that I have time slots 1, 2 up to D, where D is the maximum deadline of all jobs, because no job is ever going to go to the right of that. So initially all slots are free. So Ni is equal to I for each I. Okay? So I have initially sets of the form 1, 2, etc. these singletons up to the second singleton D, and I have f of the set j is just equal to j for every j. Now I start adding jobs, so at some point I need to add a job with deadline D. So remember our goal, we want to schedule this job as late as possible. In other words, we want to put it at the value ND, right? So what we do to compute ND is the first free slot which is available to the left of the deadline D. We check K such that D belongs to K, and we look at, so ND should actually be equal to f of K, right? So now if this ND value, if it is 0, this means that this job is infeasible. That is, there is no free slot to the left. Okay. Otherwise, we can schedule the new job at time fk, at the slot fk, right? And now we have to update fk. Now what is the new value of fk? Well, see, we had this interval and somewhere we had this set k and it was pointing to a position f of k. This was the first free slot to the left. So now the next free slot must be further to the left. So if I go to fk minus 1, it must be somewhere on this side, right? So this value, the new value, is going to be to the left of fk minus 1. Now one easy way to do this is just, so we know that the set containing fk minus 1 already tells us this value. So we just have to merge the two sets, right? So now what we will do is merge the set k with the set containing the value f of k minus 1, right? And this will have this effect. So if I take the set containing fk minus 1 and I merge the set k with that, then all of these will now point to the new value, which is the largest value to the left of fk minus 1. So in this way I proceed. So overall I will have n jobs. So I'll have n operations on this disjoint set data structure. Okay. So let's look at an example of how this algorithm works using these sets. So here we have a situation where we have 6 jobs. As always, we assume that the jobs are already given to us in descending order of profit. So we have 6 jobs and their deadlines are as shown: 2, 1, 2, 6, 1 and 6. So looking at the deadlines, we see that we have slots from 1 to 6. We add a time slot 0 to capture the impossible time slot. And we initially assigned each time slot from 0 to 6 to a separate set, a singleton containing that time slot, with f of that set pointing to the time slot itself. So this is the situation now. So k is 0, 1, 2, 3, 4, 5, 6, each a singleton set, and f of I is equal to I for each set containing the element I. Now we look at the first job. So if you look at the first job, we find that the deadline of the first job is 2. So 2 belongs to the set containing 2 in this case. So this is the set we have to look at. And now we have that f of this set is 2. So implicitly what this means is that we are going to assign job 1 to time slot 2. Now we have to update the fact that time slot 2 is no longer available for itself. And this we do by merging the set 2 with the set containing f of 2 minus 1. So f of 2 minus 1 is just equal to 1 and the set containing 1 is just 1, right? So this means that we merge 2 with 1, right? And this will give us a new picture as follows. So the number of sets has collapsed by 1 because the elements 1 and 2 have now been merged into the same set, and for that set the f value is 1. So now we look at the next job. So we see that d of 2 is equal to 1 and 1 belongs to the set 1, 2, and f of this set points to 1. So implicitly we put job 2 at time slot 1, and now we have to do the same thing. So we have to merge the set 1, 2 with the set containing f of 1, 2 minus 1 is equal to 0. And since this belongs to the set 0, we'll end up with a new set 0, 1, 2. So continuing, we now see that d of 3 is equal to 2. 2 belongs to the set 0, 1, 2, but f of this set is equal to 0. So therefore job 2 or job 3 is not feasible, right? So if a job cannot find a slot within its deadline, it's not feasible. So we will discard it and move ahead. So next we look at job 4. So now d of 4 is equal to 6 and 6 belongs to the set 6. So we'll do the usual thing. So we'll assign this job 4 to happen at time slot 6, right? This is the rightmost time slot within its deadline that is free. And now we will merge this with f of 6, the set containing f of 6 minus 1, the set containing 5. So this gives us the set 5, 6, because that set, the set containing 5 actually is 5 itself. Okay, so we will merge these two sets. So we now have this collection of sets 0, 1, 2, 3, 4 and 5, 6. So we now look at D5. So D5 is 1, but 1 belongs to 0, 1, 2 and F gives me 0. So this job is not feasible and we skip it. So finally we come to the last job. So we find that D of 6 is actually equal to 6. Now 6 belongs to the set 5, 6 and the F value is equal to 5. So what we will do is we will implicitly schedule J6 over here, and now we will update this set. So we will merge 5 and 6. So this will actually all get merged into a new entry with 4. But since we have no more jobs, we won't draw this set out and we'll stop. So actually what we have done therefore in this whole algorithm is that we have gone through the jobs in descending order and we have picked out 1, 2, 4 and 6 as our feasible jobs. There is an implicit schedule associated with it. Notice that this schedule has gaps. So I can actually take the schedule and I can shift everything to the left so that there are no gaps, because if I move to the left, optimality or feasibility is not affected. But we are really not interested in the actual schedule. We're actually interested in which jobs are compatible together, and this is a set of jobs which are compatible together, and that's all our algorithm is expected to produce. So we can now write out pseudocode for this version of the job scheduling algorithm as follows. So we start by computing the maximum deadline among all of the deadlines in the jobs. Remember, these are now ordered in descending order of profit, and so we can't assume the last job has the highest deadline. So we take the maximum deadline, and then for each of these slots from 0 to this maximum deadline, we create a separate set I with f of I equal to I. Now we start with the empty set of jobs, and for 1 to n, for each job, we first compute the set which contains that job. If the set has a feasible value as the smallest slot below its deadline, then we include this job in our solution. So we augment the set J to include I, and we merge the current set with the set containing Fk minus 1. So this is the repeated thing that we do. If we do find something which has Fk 0, we ignore it, and at the end we return the set J. Now, if you go back and look at this disjoint set data structure, so it says that any sequence of n operations takes time n times alpha of 2n comma n. Now this alpha of 2n comma n is what is called the inverse Ackermann function. Okay, and this inverse Ackermann function grows very slowly and is virtually a constant. Okay? So this means that instead of spending time n squared in order to do a sequence of n feasibility checks, over this entire sequence of operations using disjoint sets, I've actually brought down the total sum time of the feasibility checks to something which is almost linear in n. If we assume that this is close to a constant, there's some constant times n. It's not really a constant, but it grows extremely slow. Okay? So therefore we have an optimization which brings us to almost linear. Okay, so to summarize, so if we maintain J in sorted order to do feasibility checks, okay, then the overall algorithm takes theta n squared. Okay. If we use disjoint sets, then we bring it down to O of n times alpha of this 2n comma n, where this is the Ackermann function. Now, of course, there is this hidden cost of sorting the input by profit. Okay, but implicitly we assumed that the input is already sorted. So if we have to sort it ourselves, there is an n log n cost which will dominate this disjoint set cost. But if you assume that the input is already sorted, then we can disregard that, and therefore we get a algorithm which is almost linear if we use this clever representation.